This is Mars, a world that was never meant to breathe. For billions of years it's been silent, frozen deserts, thin air, no rain, no rivers. The sunlight here feels weak, stretched thin through an atmosphere that barely exists. The pressure is so low that if you stepped outside without a suit, your blood would boil before it froze. And yet, somehow, in the last decades of the 21st century, this world began to change. Mars started to make its own air. What you're seeing now isn't science fiction. It's the result of a century of patient, obsessive engineering, the attempt to teach a dead planet how to breathe. If you could stand here before any of this began, you'd hear almost nothing. The wind doesn't roar on Mars, it whispers. The air is 100 times thinner than on Earth. Even sound behaves differently, muted, sluggish, like it's moving through wool. The horizon is red, but the sky glows tan, filled with dust so fine it stays suspended for months. The first explorers who landed here brought everything with them: oxygen, food, water, power. Every breath they took came from Earth. They knew that if they wanted to stay, they'd have to build something that could produce air faster than they could use it. So they brought machines designed to do what nature never did here. The idea wasn't new. In the 2020s, NASA's Perseverance rover carried a small experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. It was about the size of a car battery, and it did something remarkable. It pulled carbon dioxide from the Martian atmosphere and turned it into oxygen. Not much, about 6 grams an hour, but enough to prove it could be done. That tiny box became the ancestor of every reactor you see today. Engineers scaled the concept from the size of a lunchbox to the size of a skyscraper. The first atmospheric processors landed in 2081. They were enormous towers, shipped in pieces and assembled by drones on the Elysium Plains. Each one used plasma reactors, superheated energy fields, to split CO2 molecules into carbon and oxygen. The carbon was stored or used as building material. The oxygen was precious. It was filtered, compressed, and stored in tanks the size of buildings. But storage wasn't the goal. The real dream was to let that oxygen flow freely, to thicken the air itself. There was a problem. Mars doesn't want to hold on to air. With so little gravity and no magnetic field, the atmosphere leaks into space. Every breath you make here wants to escape. So the engineers came up with a solution that was part science, part art: breathing domes. These weren't domes in the old sci-fi sense, no perfect bubbles with cities inside. They were living membranes, made of flexible glass composites that expanded and contracted with pressure changes. Each one created a micro-atmosphere, warm, oxygen-rich, self-contained. Inside, humidity gathered on transparent walls. Air circulators whispered constantly, mixing oxygen with traces of nitrogen brought from Earth. The sound was subtle but unmistakable, the hum of life support, the gentle hiss of a world trying to inhale. Every dome was wired into a central oxygen grid, a network of buried pipes glowing faintly beneath the soil. Together, they formed something like a respiratory system for the planet. Artificial lungs, slowly filling an ancient body with breath. The CO2 extracted from the air became carbon fiber used to build more domes and reactor shells. Mars was literally building itself from its own atmosphere. A self-feeding loop, CO2 in, O2 out, structure built from the leftovers. What began as an experiment turned into a chain reaction of progress. The more air the reactors produced, the more power they generated. The more domes they built, the easier it became to stabilize pressure. For the first time in history, humanity wasn't importing life to another planet. It was manufacturing it on site. The next step was biological. Machines could only do so much. Engineers turned to one of the simplest, oldest life forms on Earth: algae. Dense, green, efficient. resilient. In massive transparent vats, the algae floated in nutrient-rich water, converting CO2 into oxygen 20 times faster than trees. They were illuminated by a soft white light that mimicked daylight cycles from Earth. From orbit, those bioreactor domes glowed like emerald lanterns against the red desert. Inside, the air smelled faintly of metal and salt. Tiny bubbles rose through the liquid as the algae exhaled oxygen. This was the first time biological life truly returned to Mars. Not transplanted forests or animals, but microbes and plants engineered for this alien sky. Beneath the surface, scientists grew colonies of bacteria that survived in low pressure. They fed on iron and sulfur and released trace amounts of O2 as waste. Layer by layer, Mars was learning how to host chemistry that supported breath. By 2095, the network stretched for hundreds of kilometers, thousands of reactors, condensers, and algae domes connected by buried conduits. Drones roamed constantly between them, repairing, recalibrating, reporting. At night, the only sounds were mechanical. The deep vibration of turbines, the occasional crack of frost, the rhythmic heartbeat of compressors maintaining internal pressure. Every molecule of air was monitored. Too much oxygen, and the domes risked over-pressurizing. Too little, and the biological systems would suffocate. Mars demanded precision. There was no margin for error. It was a planet-sized experiment, running on the edge of failure. Then, something changed. A cluster of pressure sensors in the Elysium Valley detected a rise, a barely measurable thickening of the atmosphere outside the domes. It wasn't just localized leakage, it was diffusion. The oxygen was escaping, yes, but it wasn't vanishing into space. It lingered. For the first time, the planet itself was beginning to hold air. In the early mornings, explorers began to see faint fog collecting along the valley floor, thin threads of moisture that twisted in the cold sunlight. It wasn't rain or clouds or anything familiar. It was vapor, born from condensation inside the domes, escaping and surviving in open air. Mars had made its first weather. When that image reached Earth, mist moving across a Martian valley, the world paused. It wasn't spectacular or cinematic. It was subtle, quiet, almost ordinary. But in that ordinariness was something profound. For the first time in billions of years, a planet that had been dead was participating in the cycle of breath. Inside the domes, the technology kept improving. Solar farms provided almost unlimited energy. Algae produced not just oxygen, but food additives and bioplastics. Methane captured from waste-powered heat exchangers. The system became a closed ecological loop. Air, water, carbon, energy, all cycling endlessly. Nothing was wasted. Outside, new experiments tested open-air reactors built into deep craters. Their design allowed them to trap gases under natural rock basins, using Mars itself as a containment shell. Slowly, the atmosphere thickened. Pressure rose by fractions of a percent each year. It wasn't enough for humans to breathe unaided, but it was measurable. Mars was becoming stable, not habitable yet, but sustainable. But progress on Mars is never smooth. Every success came with setbacks. Dust storms, those vast planet-wide events that can block sunlight for weeks, shut down solar farms and buried vents under meters of dust. Power grids failed. Reactors froze solid. Engineers had to build new protocols, autonomous bots that cleared panels, self-heating cables that melted ice, backup nuclear batteries that powered life support through the dark. Even then, failures were constant. Valves jammed, pipelines cracked under thermal stress, but the system learned. Artificial intelligence took over routine decisions, adjusting pressure and chemistry faster than humans could react. Eventually, the network ran itself. Humans became the visitors, not the managers. When you stand inside one of the major domes today, you don't feel like you're on Mars. Not immediately. The light has a soft golden tint, filtered through dust, that diffuses sunlight into something almost Earth-like. The air smells faintly metallic, with traces of ozone and mineral dust. It's dry but breathable. People walk without helmets now, at least inside the domes. You can hear footsteps, conversation, the low buzz of systems working overhead. Step outside, though, and the sound vanishes again. The silence reminds you where you are. Mars isn't a second Earth. It's a machine we built to host us. None of this came cheap. Every kilogram of equipment that left Earth cost millions. Every ton of oxygen produced required energy, logistics, and years of testing. And yet, when you think about it, the math is extraordinary. Humanity spent centuries learning how to burn oxygen. On Mars, we finally learned how to make it. Each reactor, each algae dome, each filter represents the sum of our curiosity. They're not monuments, they're lungs. From orbit, Mars looks different now. The polar regions shimmer faintly blue, where atmospheric density has increased. Around the equator, glowing networks trace the reactor fields, like veins of light beneath red dust. If you listen to the microphones that explorers left behind, you can hear it. The soft hiss of wind, the low vibration of turbines, and, rarely, the sound of something else. Thunder. Not the kind that shakes the ground, but a delicate crack of energy in the air. The sound of pressure equalizing through an atmosphere that didn't used to exist. That sound, barely audible, is the voice of a planet that's breathing. Mars still has a long way to go. The air outside the domes isn't truly breathable yet. Radiation levels are still high, temperatures still drop below -70 at night. But inside this network of machines, life persists without constant help from Earth. That's the miracle. We didn't just survive here. We built a system that made survival possible, one that turns sunlight, dust, and carbon into air. And if you think about it, that's what life has always done. On Earth, microbes turned a poisonous atmosphere into the one we breathe now. On Mars, we're doing it again, on purpose. Maybe that's the real continuity between worlds. Not water, not land, but the act of turning chemistry into breath. If you stand at dusk near the old Elysium reactors, you can see the faint blue shimmer of light above the horizon. Scattered oxygen molecules catching sunlight. It's thin, fragile, but it's there. The sky isn't silent anymore. Listen closely, and you might hear what Mars has become. A world that hums softly to itself, each machine breathing in time with the others, each pulse a small reminder that even here, in the cold vacuum of space, life can find a rhythm. That's what makes this a miracle, not because it's impossible, but because it's deliberate. We made this planet inhale. We turned physics into weather, dust into air, silence into wind. Mars breathes now, not perfectly, not endlessly, but enough. Enough for us to take off a helmet, draw a breath, and realize that a world that was never meant to live has found a way to. Maybe that's what we do best as a species. We give dead worlds a heartbeat. And in doing so, we remind ourselves how precious it is that our own world still breathes back.